Now we will see how we can use treasury futures to manage interest rate risk. So the idea is that we are managing a portfolio of bonds. We expect interest rates to change in the future, and we may want to adjust the duration of the portfolio. So the idea is that we are going to add these treasury bond futures to our portfolio in order to achieve the duration that we want. Okay. So you would expect, uh, at least the first time I looked at this stuff, I expected that the way to use these treasury futures for hedging would be pretty clear, very well known, and simple. However, it's not. As I discuss down here in the notes, there are different approaches for how to use interest rate futures for hedging. Okay, so different books, different sources will give you different formulas for how to actually trade these treasury futures. The formula I'm going to show you here is the one that is shown on the CME page in some paper that they have there discussing how to use this contract. And it's a formula that I think makes sense, that I can understand, meaning that I can actually derive the formula and see what are the assumptions that are going on and exactly how we get at these numbers, right? So here's the idea. If we are managing a bond portfolio and we want to fully hedge that portfolio, meaning we want to make the duration of that portfolio become zero, what we need to do is we need to trade treasury futures in this amount. So what I have here on the left-hand side is the notional that I have to trade in the futures. And what we are saying is that the notional will depend on this ratio, where V is the value of the portfolio right now that I'm managing. D is the duration of the portfolio, again, that I compute right now. And then this lower part is related to the futures. So B is the price, the current price of the bond that I expect to be the cheapest to deliver in the future, the futures. D is the current duration of that same bond. And C is the conversion factor of that same bond, okay? So the proof is done here. I am not going to go through the details here in the video, but we can discuss this if you have any questions. I go instead to show this with, I'm going to show this with this example here, okay? So let's think of a fixed income manager that is managing a portfolio of bonds again, okay? And the idea is that the bonds that he has done well, there are considerable capital gains on the portfolio, right? However, at this present time, let's say it's October, the manager expects interest rates to go up in the coming few weeks, right? So this is bad, as we already know. If interest rates go up, bond prices go down. That will create a loss for the portfolio. Okay, he could sell the portfolio now and buy it later on, but that would be bad for these tax reasons that we discuss here. Okay, so instead of selling the portfolio, what he's going to do is he's going to manage the risk by trading interest rate futures, and therefore he does not need to sell and then buy back again the bonds, right? Okay, so let's say that the current portfolio is worth $10 million and has a duration of 8.55 years, right? So this means that the bonds that we have in the portfolio are not that long, so it makes more sense to use, rather than that very long treasury bond futures, actually use one of the shorter contracts that we saw when we discussed the contracts that are actually trading on the CME in the previous video. So in particular, we are going to use the 10-year treasury note futures. Okay, and as we said before, they work in exactly the same way. So we estimate that the cheapest to deliver is a given bond that has a price like here, 97%. It has a current duration of 9 years, and the conversion factor is this number, all right? So the notional that we need to trade is just applying that formula that we see up there, but this is just plugging in the numbers. But anyway, let me show you. This will be the number. So again, this is the formula. This is the value of the portfolio and the current duration. And then this is the bond that I expect to be the price of the bond that I expect to be the cheapest to deliver and its current duration. And this is the conversion factor of that bond. So doing the ratio, we get this number here. The minus sign means that I need to short the contract, the futures contract. So the trade again is to short this amount of notional, or rounding to the size of the contracts, I should short 67 contracts. Okay. So let's see that this does indeed work, and under what conditions does it work? Okay. So the scenario is the following. Let's assume that we have an instantaneous parallel shift of 0.2%, an increase in rates. Okay, this was the bad scenario that the manager was worried about, interest rates going up, and that's exactly what happened. So if everything works as intended, the loss in the underlying bond portfolio should be compensated by a gain in the derivative. Okay, that's the perfect hedge. So let's see if that is the case. So again, the assumption, changing rates of 0.2%. Recall the formula for the duration that we have used many times already, but again, I write it here. So let's first estimate what is the change in the value of the underlying portfolio using this duration approximation. Okay, so the value of the portfolio was $10 million and the duration was 855 years. So times the change in interest rates. Again, I'm using this approximation that comes from this formula. The change in price is on the left-hand side, and then we have duration times price times the change in rate. Okay, so this is nothing new. We have seen this many times before. It's the usual first-order approximation, right? So we have a change in value of minus this amount, minus $171,000. So that's the loss. So now let's see if the derivative is doing what it should. So let's look at the futures. So first, what happens to the bond that is the cheapest to deliver? Well, again, using this approximation, the change in the bond price, dP, and here we're calling it delta B, is approximately equal to minus the duration. Recall that the duration was this number here. This was the price, and this is again the increase in interest rates. So the bond price will decrease by 175.98%, right? Now, here's the crucial thing. The assumption of this formula that we saw for the hedging amount is that the basis remains constant, meaning the difference between the market price of the bond and the price of the bond under the futures contract, which was this F times C expression that we saw when in the previous video, right? This difference remains constant. So if the bond changes by an amount, the futures will adjust by the necessary amount to keep the basis constant. So for the change to be zero, right? So if the bond price changed by that, the futures price for this to happen has to change by, solving for delta F, we get that the futures price has to change by this amount here, right? Okay, so then what is the payoff to the short futures? Well, it's the usual expression, notional times the change in price, but notice here that I am doing the short side. So I am flipping the signs relative to the usual expression for the long side. So this is the final price at which I sell, okay? And I have a plus sign here in the beginning, the price at which, sorry, I'm saying this in the other way. So I have a minus sign in the end, which is when I close the position, so I buy, and I have a positive sign in the beginning, which is when I sell in the beginning, okay? Again, because this is the short side of the futures. So this is the symmetric of the typical delta F, so I put a minus there, okay? Minus with a minus cancel, so I have a positive number here. So it's the notional that we had defined in the previous example, right? So the notional that we're trading times the change in the futures price like this. Okay, so this becomes a positive number of $171,000. So this works exactly as it should. The change in the portfolio is exactly compensated by the change or by the payoff in the derivative. So the two, 1 plus 2, this plus this, add up to 0, which is the perfect hedge. Okay. All right, this formula that we just saw was a total hedge in the sense that we were setting the duration of the portfolio to 0, okay? In practice, asset managers may not want to do that. The idea is that they are usually benchmarked, and if they decide to change the duration by a lot and they are wrong, then they may deviate too much from the benchmark. So what they may be allowed to do may be limited. So they may only want to change the duration by a given amount. So if that is the case, we can modify the previous rule to have a partial hedge rather than the total hedge. So the difference now is that we now have here a target duration, right? So we are not going to put the duration to 0. We are just going to put it to some target number, which may not be 0, okay? So in fact, the previous formula was a special case of this one when the target was 0, right? So a very quick example. Suppose that it is the same portfolio that we are managing, but now we expect the opposite. So we expect interest rates to go down, right? So if interest rates go down, we will benefit from an increase in the bond price, right? So if we want to bet on that, we want to increase the portfolio duration, okay? Suppose that we are allowed to increase the duration up to 12 years, right? So the target duration here will be 12. Okay, so now we need to go to the futures market and actually trade on the other side to increase the duration of the portfolio, right? So now we are going to buy instead of selling futures contracts. By how much? Well, just plug in the numbers here. Everything is exactly the same as in the previous example. The only difference is now that we have a target duration that was 0 in the previous example and now is 12, all right? But the numbers are the same. I'm not going to do this here, just plug in the numbers and you should easily find that the result now is to buy 27 contracts, and that will increase the duration to the desired level. Okay, and that's it. Thank you for watching.